So, you guys heard a lot about WDL and Cromwell in the past few days. This is just going to be a sort of overview of what you already know for the most part. So, the goal that we strive for when we develop these pipelining languages and backends that are able to run them is to be able to automate things that we run on a daily basis. So we want to be able to take a set of commands, say GATK commands, put them in a nice readable workflow, and then just be able to, with one click of the button, execute it and be able to reproduce that result. We also want to be able to, we want it to be deterministic, right? We want it to get the same result. We also want to be able to take advantage of things like call caching when something goes wrong during execution, and we don't want to restart the workflow from the beginning. We want to kind of save everything that we've done so far and resume from that point. And we also want it to be modular so that we can have, there's this part of the workflow that does pre-processing, part of the workflow that does variant calling. We want to be able to put them together in a nice big workflow that would do both. So this is what WDL, Cromwell, and Terry is trying to accomplish. So the basic structure of the WDL looks like this. This is your, on the right, on top is your WDL, typical WDL workflow. You have a unique name that will be used for referencing this workflow. On the top you have a list of inputs, and these inputs are typed. There are several types that you can find in the WDL documentation that are supported, and this will correspond to your JSON input. So the stuff that you will put in your JSON as input to your workflow, as you will see later, will correspond to these guys for the most part. And then you have a bunch of tasks. So for example, these tasks A could be something like haplotype caller, and you say called haplotype caller with these inputs, which is like my reference, my BAM, blah blah blah. And then you also have to define a haplotype caller task, which will look like have a structure like this thing on the left. So let's take a look at that. You also have the inputs, which are also typed. Then you have command block. So that's kind of where the meat of the task goes. The actual command line invocation that you would, where you put something like java-jar GJK, haplotype caller, and all the other parameters. So that would be your bash command that would actually get executed once you spin up your machine and copy files and so on. Then you have you have output block, so that will basically declare to the WDL, to the actual Cromwell server, that you are expecting a certain output. So for example, here you could have a VCF of that haplotype caller outputs, and the system will be aware of that. If you don't put it there, it will not be copied over. So everything that you put in output will be eventually copied somewhere into your Google bucket and saved. So it's important to remember. And finally, you have this runtime block, and this is pretty useful for defining things like memory usage, CPU, and when you give the these parameters for the runtime block, the Cromwell server will be smart enough. If you're running, for example, on Google backend, it will be smart enough to say, I want to spin up these particular machines with this much memory and this much CPU. And finally, you can also point it to a Docker that you want to be running on. And you can define a bunch of different tasks, and then you can string them together. And actually, for example, final thing is that you can reference outputs of one task in the next task. So for example, right here you have as input the output of task A. So it will run task A, it will produce this output, and then we'll grab it and push it to the next task. And in fact, it's smart enough if you would put this invocation before this one, it will still be fine. It will not break things because Cromwell will figure out that in which order to run the tasks. Or if it's just if there's some kind of cycle in your graph, then it will break things. So you have a few different options for plumbing in WDL. So you can have something straightforward like we just saw, that you call one task, it produces some outputs, you push it into the other task, it produces some outputs, and so on. So kind of like haplotype caller. You can also, it doesn't have to be just a single output file, it could be multiple output files, and you can put them both in as input to one task, or it could be one could be input to one task, one could be input to the other task. Well, basically, with these two ideas, you can write most of the workflows. One other things that will allow you to do is to do what's called scatter gather, and this is used, for example, if you wanna parallelize your computations in one way or another, whether it's over samples or across reference. You can have the scatter block, right? So for example, let's look at this code. You are given an array of files and input files, and then you have the scatter block, which you can for a second think of it as a for loop, but it's not a for loop. And then you say scatter for each file in this array, and call a task with this file as input. And finally, when you're done, what this entire block outputs is another array of outputs. And then you can call some other task with input with this array of files as input, right? So we'll also take a look at that later. Yeah, I mean, a few other things to mention is there's things like if blocks, which allow you to evaluate certain expressions and run certain tasks conditionally. And that happens it happens on a Cromwell server, so you don't actually spin up any machines. You just Cromwell server figures out which evaluates the conditions. It will call certain tasks, and it then will spin up your machines.
So are the input files implicitly if blocks, in the sense that the step would be executed only when the input files are available from the previous tasks?
You can do it that way. You can say if this file is sort of defined, then execute these tasks with this input. You can do things like that.
And similarly, similar to this scatter-gather scheme, but if there are multiple steps which could be run in parallel, followed by another step. whereas in this example we have like one step on multiple input files,
Mhm.
but would you have like other scatter-gather kind of possibilities where you have step A, step B, step C running in parallel?
I see. Yeah, you can. So scatter block. Inside of scatter block, you can have like call step A, call step B, and so on. Yeah, that's fine. And it will parallelize. So it will. So these, if you say call step B, call step C, those will run in sequentially, but it will run. It will run. It will parallelize across these files.
So for example, you imagine you have in the best practice workflow, we start by analyzing each sample independently, doing the pre-processing and then the initial variant calling as per sample. That's one pipeline. But then you want to parallelize, you want to run that across multiple samples. So you can set it up with a master whittle that says, for each sample in my set of samples, I can run that pipeline in parallel. And so you can have multiple layers like that. And you can even import a whittle inside another whittle. So you can have something that is an elaborate pipeline in this block. And you can have nested scatters as well.
So is it fair to say that parallelization is over the files usually rather than over the tasks?
There's two main modes of parallelization. I would say is over the files, so over the samples, but it can also be over genomic regions. So let's say you want to parallelize over exome intervals or chromosome or something like that. You can also use the same code, but instead of iterating over a list of files, you'll iterate over a list of intervals. Yeah.
So it doesn't accept the wildcards. You have to write a loop for input file.
No, it's not a loop. So it's not a loop. It's really, it's saying, well, it feels a lot like a for loop because you're basically saying for each file in this thing, do X. But you don't have to wait for the first one to be done. Like a traditional for loop, you have to wait for the first element to be over before you start the next one. In this case, if you have 50 machines available, you start 15 workflows, 15 tasks at the same time. And that's where working on the cloud really takes advantage of that, because you can parallelize pretty much as widely as you want.
Do you have to explicitly name the output variables? Because it always looks like step A out. Is it like a standard notation?
Yeah, you name it.
You have to name it, but like, can you go back to the previous one? So here we say dot out. It could be any arbitrary words that you want. So you can say dot output file or dot Jessica. It's the same thing.
Does it support like this wildcard expansion? Wildcard expansion.
It supports
Yeah.
supports it in here. Yeah.
And so you can have things be named automatically. So you'll give a variable name, but then inside of that you can create. And there's a few, not to get ahead of ourselves, but there's a few like built-in functions in the language. So you can do, for example, just get the base name of the file, strip the path, strip the extension, just get the base name. And so if you have myfile.bam, you can have myfile.vcf come out, stuff like that.
I have a question. So, like, say for example, from a process, if you're getting like multiple outputs, so do you have to like specify each output separately, each output file?
Can you clarify?
Say for example, for the BQSR,
Mhm.
when you get a transist file, you get like this R script file, RTF file, and other files. But for the applied recalibration, you use only the transist, so you don't use the R file. So you have to like specify everything separately.
There's a couple of ways you can deal with that. If you're naming the files explicitly in the command, then typically you would name them specifically in the output as well. But if you have a program that's generating 50 output files and you're not naming them directly, what you can do is use a blob, which is basically saying capture everything, and you can do that based on some regular expression or just everything that's produced as an output of the task, you can grab all of that and export as a
Yeah. So if for example you output like VCF and a BAMA, then you will have two outputs here, two files, and then suppose you have like a folder with a bunch of plots, you will say it outputs an array of files, and then you would call the standard library function glob and say grab everything in plot directory.
Okay.
So yeah.
Yeah. So if I give a log function to output all the files, and if I want to use like one specific file for the next, like maybe after 3 process, so should I name that one specifically and rest like use a log pattern?
Yeah.
Okay.
Yeah, if you want to use that one specifically, otherwise what you have to do is pass that glob to the next task and tell it how to identify the output. So at some point you have to tell it like how to find that one file that you want it to find. There's a couple strategies, but if there's the one that you really care about, it's definitely worth naming it explicitly to simplify.
To the multi-sample, I think it's meant for one sample processing. So one sample has all the BAM files and then BAM files and then the start project. So then if I have to start with multi-samples, where can I start checking the things?
Yeah, so I mean, if you have, if you're trying to, so the way we do it, right, is that we have a workflow management utility. Either you're using Terra and you're just saying for all of these things, run the workflow on each of them. Outside of that, in production, we have a management utility, kind of a dashboard that allows us to do the equivalent things, so we don't have to script it. But we have a way to say, run our standard pipeline on this set of files, and that's handled by, it's tied into the Linux system, so it's an extension of that. But if you wanted to do it by yourself, you have a standalone Cromwell server, and you want to run that, either you write a bash script, or what I would recommend is then you can write a master WDL that says import the processing pipeline and do a scatter on your files. And so at that point, all you need to do is specify an array of the inputs samples, and then like that way. If that makes sense.
So this, like for example, takes one BAM, and then you can have another workflow that says call my workflow with, and that big workflow takes a list of BAMs, but then it calls this workflow with only one BAM.
So we have, one of the things we'll show you at the end of the session is that we have a set of what we call WDL puzzles, which are kind of like take-home exercises where you have some, it's like one type is a WDL that's incomplete, and you have to do some, like fill in the WDL to finish it. And the other one is, like you have a basic WDL and you have to improve it and optimize it. And one of the optimization steps is actually to do basically that, of taking the pipeline, import it, and run it across multiple samples. So we won't go through that exercise, but the solution is included. And I think that'll give you an example
That would be great actually.
of how you would do it, like basically the recipe.
So we don't need to run all pipeline once.
Yeah, yeah. No, you don't have to go and hurt your finger clicking.
So one of the very useful things to do is to Google WDL standard library, and there you have all these bunch of different commands that you can run inside of your WDL itself. And basically, you can do like most things that you can think of doing. Like you can scatter whatever ways you would think of scattering and so on. And most of the things you can imagine are supported.
I'll give a caveat to that, which is that WDL is really designed to express workflows, right? It's not designed to do a lot of processing of the data within the workflow.
Right.
So if you want to do complicated things like loading in an array and like as part of the WDL but not a task, like load in something and then sort your array and then do various things, take out elements, and then run things on that, run a task on that, you're going to run into some limitations because it's not a general purpose programming language. It's not Python. It's not Bash. It is really meant to express the workflow, and anything that takes some amount of work to do, to handle the data and do something to it, you want to encapsulate that in a task. And so that's kind of the paradigm for how the language works. And so compared to something like Python, for sure, you'll have less flexibility. But that's because that's not what it's designed for. If you find yourself wanting to do something like that, you can actually write inline Python within a task. You can make a task that will run some Python code to do that transformation, that handling. And the goal really is to separate expressing the workflow and doing the work. Kind of like in web design, you want to separate the structure of your website and the content that you plug into it. It's very similar for when you're running an analysis workflow. You distinguish the plumbing from what you actually put through the plumbing, if that makes sense.
So these are the runtime block that I was talking about before, and as I said, you can define various parameters here that let the backend server to set up the machine that you need for you. For example, you can provide the memory requirements, CPU, disk, Docker image, and there's this field for preemptible. So that's what we talked about the other day with having much cheaper machines, but they can be suddenly stopped during the execution and taken away from you. However, they cost 5 times cheaper. So for the most tasks that run for less than 3 hours, this gives you 2-3-fold savings or something like that. Let's see. Yeah, that's.
Does the runtime block support the Anaconda environments?
No, that's just the Docker. Actually, I don't think so. No, Well, inside of the Docker, you can install whatever Anaconda environment you want, but. So the overall paradigm is that you write a WDL, and then this WDL will run inside of the Cromwell server, and that Cromwell server has different options for a backend. For example, you can run it locally on your laptop or some kind of SG cluster or any other type of on-prem cluster, or the option that we use support is you can run it on Google Cloud or AWS, and there it will set up all of the machines that you need to be using, all of the compute, and and so all is done seamlessly. So there's two execution modes of the Cromwell itself. One is what is called one-off execution, where you just run your WDL once, and then at the end the server dies. And this is good for developing WDL. So if you want to develop your own WDL, that's what you would do. You would just make your WDL, make your JSON input with some sample inputs. You would run it locally, and then you would convince yourself that it works, and then you would put it up on a cloud. And there's another mode, which is server mode, which is what we use for Terra, or you can also use it for other backends. And this mode allows you to do a lot more things, and it's optimized basically for production environments where you have many workflow request incoming, and you want to be able to schedule jobs as they income and not be waiting for the results. And this server has many useful API endpoints, including, for example, you can request your workflow to be run. You can query it. You can see what the status is, what the timing is, and so on. And finally, you also have call caching, where you basically have a database set up with the results of your workflows, with the location of where your previous results of your executed workflow steps were, and so in case if you have some kind of failure of your workflow due to some typo, for example, at step 5, and then you fix it and then you rerun it, then the Cromwell will be smart enough to say, well, I already executed everything up to step 5. Just let's grab all the outputs from the previous execution and continue on. So when for the one-off execution, you have a separate tool set that allows you to validate that workflow. This is super nice because you probably gonna have some typos or bugs, and before you don't want to be just like running and fixing bugs. So this is a very easy way to see if your WDL syntax is actually correct. So there's a separate one tool that we can point you to, which you can run on your WDL. It will tell you if there's bugs, you fix the bugs, you run it again, and so on until you have no bugs. There's another WOM tool option. So WOM tool comes with bunch of different commands. These are just 2 of them, which are really useful. And so this inputs command allows you to give you a template JSON file. So if you have a big WDLs, for example, for running headless app caller with like 20 inputs, you don't want to just write your JSON file from scratch. You run this command, and it will give you the input JSON file template, and then you just fill in the inputs. And finally, you use the Cromwell jar to run this WDL with the input that you generated in the one-off mode. So that's what we're gonna do today for the first part, and I think this is it.